Thank you for the invitation. It's a great pleasure to be here. At least for me, that's a sort of a new community. I know very few people, but many I don't. So I have the impression that most people do not know much about rough paths. So for that reason, I've tried to keep it very basic. So I know that a few people are, of course, specialists here. Anyhow. I had to dig a little bit in the past and find examples at various bits and places where there's a link. So let me start from something which I would call the rough path principle. And it's the following situation, which I believe is very common, namely, you have some problem that has noise. So you can think of Brown motion or white noise. There's an equation that you have to deal with. You can think of a stochastic differential equation. And here, these could be the coefficients of that equation. And then what you want to do is solve the stochastic differential equation, so there's a notion of solution, or hopefully there is. Okay. And it is very commonly, and I will give you some examples in a moment, the case that the solution map here, which is called the Ito map in the context of stochastic differential equations, is well posed when you look at mollified noise, and when you look at the actual thing you're interested in, say Brown motion, then as a probabilist you say, okay, it's well posed, but if you think about it, it's actually not, because that's Ito Stratonovich, and depending how you approximate, many things can happen. Okay, so let me just say here, there is a classical solution map, which is continuous, at least for mollified noise or smooth noise. But it's not continuous, not robust for the noise you're interested in, for genuine noise, okay? Okay, so let me give you a few examples here. And the first example is, I will come back to this principle in a second here. There's a part of this picture which is missing. But first I want to give you the example here. You have a noise of the form B is a Brown in motion, B, and then we mollify it. So this is mollified Brown motion, and now put a dot, so then it's mollified white noise if you want. And what you can do is you can solve a simple ODE, solve this random ODE, which is just of the form y dot equals f of y, and then b dot epsilon. Of course, y depends on epsilon. Initial data is fixed. I don't want to write it down here. And also remark that my notation may look scalar, but everything I'm saying sort of works in a multidimensional setting. That's a generality, which is, of course, crucial here. And then the question is, what happens when epsilon goes to 0? And, well, as many of you will know, what you get is that in the limit you see a Stratonovich equation. This is one example to have in mind. Now, here, you still get a measurable map for Brown motion to the solution of this diffusion equation, but that's the notorious lack of regularity known in literature, that this measurable map from Brown motion to y is not continuous in any topology in path space that supports the Wiener measure. So here's some sort of... Pardon? So I wrote it here, but perhaps too small. So think of B is a Brown motion, B dot is white noise, epsilon is smallification. So convolution with a, rescaled, compactly supported modifier kernel. Yeah, you could do piecewise linear for approximations if you want. Doesn't matter. Right? So, this discontinuity has been a problem in many situations. Now, there's a picture here. If you could take your noise and lift it to a bigger space, let's give it a name. Let's call it, chi. And the equation, let's just copy it here. I'll need it later. Then here again, you get somehow perhaps an enhanced solution. And then here you project, if necessary. So what's going on here? If this map here is not continuous, perhaps you can factorize it in a way that you see where this lack of regularity comes from. And you can do this in a very precise way. So there's a lifting map, let's call it capital psi, which is again not continuous. So like that's here. But once you did this preliminary step, life is good. And as a function of this enhanced noise, and I have to be explicit sooner or later what I mean here, and it depends on the context, you may be able to construct the solution in a robust way. So here's an enhanced solution map. And this one is continuous, and that's the whole point. Right. So whenever you can find a situation where this diagram works, let's call this the rough path principle. And until a few years ago, there was rough path theory, and you could draw this diagram, but it was sort of clear. But now we see increasingly many examples where this happens. So in this context here, but I'll come back to this, it would amount to take Brown motion, to compute the first iterated integral. This gives you the enhanced noise, and as a function of this enhanced Brown motion, this eta map becomes a continuous and even locally Lipschitz map. Now, I want to give you a few more examples here. So let's go up here. I have to speed up a little bit. The second example I wanted to give you is filtering, which I think gives a very good motivation why you care about this, not just for mathematical convenience. So assume you have a signal process, and I'm not going to write it down, some diffusion dynamics. And then there's an observation process. Which you may assume is of the form, h of y dt, so something depends on the signal, of course, plus some additional noise, which may or may not be correlated with the signal. And you're interested in the PDF of the signal given your observation. Now, if you had no observation and you just want to study the evolution of the density, then you just have to write down the Fokker-Planck equation. But here in this case, this becomes a stochastic partial differential equation. So the interest in the PDF of the signal yt, say, given the observation. Yeah. And what you get is that Sakai, well, I simplify a little bit. There's some normalization which I don't talk about. But essentially, to solve this problem, you have to solve the following SPDE, which is of the form partial t u equals L star u, which is the adjoint of the generator of the signal, plus, and then there's another guy here, let's call it gamma u. So this is a second order. This one's a first order operator. And there is some y dot here, okay? And I would really, if I wanted to write it in differential form, I would want to think of this as a Stratonovich differential. Okay, now I see the problem. This is much more complicated than just a silly ODE or SDE. This is an SPD, and you have the same problem. You want to understand what is the regularity of y maps to u. Why do you care? Well, this is a big theme in filtering. It's called the robustness problem. As an engineer, you would very much like to know that your conditional PDF depends in a robust fashion on the observation. I'm sorry, there's a Z here, right? It should depend in continuous, robust fashion on your observation, otherwise what are you doing, right? So robustness is this question, what do you know about this map here? Okay. Now, the next example I wanted to tell you is, but I'll keep this very short. I mean, if you know stochastic Löwner evolution, a sort of similar picture. You have a Brownian driver, square root kappa times the standard Brown motion, and you map it into these SLE curves. And if you want to know what is the regularity of this map that takes the Brownian driver and maps in this SLE curve, you will find yourself here exactly in this picture, actually. Right? So what is the precise lifting is an interesting problem that some people are working on. But let's keep this short here. The next one is, let's say, singular SPDs. I mean, this here was a linear SPD, so even here's a question, but singular SPDs are much worse. Think of something like KPC. So here you have space-time white noise, 1 time plus 1 space dimension. So 1 plus 1 dimensional space-time white noise. And as many of you know, this is a very nasty SPD that people didn't know much what to do about. And when Martin Heira proposed his solution to this problem, the picture that he drew was exactly this here. Now the difference here is you're not going to get away with a simple rough path space where you put in some iterate integrals. You have to construct your space chi. You have constructed from first principles from this equation itself. So the way to do it is start some formal pk iterations, see what sort of expressions pop up, and make sure you keep enough of them as abstract elements in your space that you can do something. So I may or may not say a little bit more about this later. And 5, fully nonlinear SPDs in the sense of Souganidis, Lyons Souganidis, and Taki spoke about this yesterday a little bit. So the SPD examples where you also have some rough dependence here, and the problem here is not only to understand the robustness, but actually also to define what do you mean by solution when in this rough regime. Good. So this is all very soft here. Let me be a little bit more precise. So I'll come back to this ODE, SDE picture in detail in a few minutes here, but let me head straight for So what has any of this to do with homogenization? This list of examples here is a selection and by no means exhaustive, and we'll see more in the next talk. But the first one I wanted to talk about is a class of symmetric diffusions, multidimensional on RD, and let's call it Xepsilon. And the only thing I tell you is the generator in divergence form, which I am assuming to be of the form partial I AI j dot divided by epsilon partial j. So I suspect for this community this is very familiar. So this matrix A here is symmetric, uniformly elliptic, periodic. That's a question of taste if you want to assume some regularity or not. Let's, for now, assume sufficiently smooth, because in that case, you can construct this process by solving an SDE, and of course, then you get the same martingale structure. Right? But you don't have to do this. I mean, you can construct this directly using Dirichlet form theory. Okay, and then it's a very classical fact that X epsilon converges weakly to Brown motion. So B is a Brown motion. The covariance structure may not be trivial. It will have to do with the averaging of, this A over a cell. So with covariance A bar and okay, and if you want to put a 1/2 here, you can, but let's not worry about it. Okay, so now let me consider the following add-on to this problem, namely, let me go back to the problem of solving some sort of stochastic differential equation, well, not only some sort of, a stochastic differential equation, driven in Stoyanovich sense by dx epsilon. Okay, so initial data again fixed, and of course then you get u equals u epsilon. And the only reason I wanted to point out here that you can get the same martingales, then I don't have to worry about the meaning of this equation, right? So now it's a well-defined stochastic differential equation, makes sense in the same martingale framework. And then you can ask yourself, what happens to, what do you know about the convergence of these guys here? And, well, you would hope, and that's the question here, that you get in the limit dy equals fy Stoyanovich dB, where again B is understood as this B here with the correct covariance structure. Yeah. So the question, I mean, it's a well-posed problem. You can go ahead and just try to prove it. The answer is yes. But the strategy of proof is very elegant, namely, so the answer here, I'm just giving you the idea, is to understand, it's a way of doing it, I'm just claiming it's a particularly elegant way to do it here, understand X epsilon converging to something in chi, right? So if you can manage to show that your drivers here converge, weakly in the sense, in the space of enhanced noise, then I can just use my stability property of the solution map as function of the enhanced noise to conclude, right? So perhaps not the answer, but towards the answer. The second one I want to talk about is, and let me move over to the other blackboard so I can keep this for later. The second one is what I call physical Brown motion. B, physical Brown motion. And here, what I have in mind is something, you know, the Newton law tells you that change of momentum equals to the forces here. And if you assume that there's some unit friction here, then this is your dynamics. And if you subject the whole thing to white noise, so let's model it by B dot. So this is white noise. Then that's how it looks like. And if you try to make this multidimensional, then, you know, having friction in the x direction, maybe friction in y and z, and you may rotate the axis a little bit. So the general picture is that you have a symmetric matrix here that models your frictions, which may be different in all these directions. And now a little remark here. If you assume that your particle carries some electric charge, and you assume there's a constant magnetic field around, then the Lorentz force kicks in and effectively tells you that this matrix here will not be symmetric anymore with positive eigenvalues, but it will have an antisymmetric part. So in presence of magnetic field, plus of course a charge on the particle, otherwise it wouldn't feel it, you get that this goes both ways. Okay, so this is dynamics we're interested in. And, well, simple things first. If you let mass go to 0, so just set it to 0, you see that mx dot equals p dot. You integrate it up, so modulo starting points, you see that x will be a Brown motion, perhaps with a non-trivial covariance structure due to this matrix here, but again, let's not worry about this. I mean, there's nothing to worry about anyway. So you have clearly that x as a function of your mass parameter, when mass goes to 0, should converge to B. Again, Brown motion with a non-trivial covariance structure. Depending on, I mean, okay. Okay, and moreover, if you look at it, xm will have continuously differentiable sample paths. So let me just say it's C1 plus, I mean, a little bit better sample paths. Because in the end of the day, you have Ornstein-Uhlenbeck dynamics for x dot, and then x, you integrate it up, so you will have, 1 plus diffusion regularity, C1 plus. And in particular, you can ask the question now, again, what happens when you let this guy interact with some subsequent differential equation? So dxm dot here, this is really an ODE. So I could have written it, could have written it as y dot equals fy xm dot. And the question is, when m goes to 0, oops, what do you get? Well, smooth approximation. The question is, do you see in the limit something like dp? Okay. Of course, the right Brown motion with the correct covariance structure. Good. And towards the answer, what you should do is, again, understand this guy here in this mysterious space chi. All right. And assuming it does converge, and it converges to some lift of Brown motion that yields the solution, then you're done. Right. Now, time is running, so I will not go back to this KPC example. Suffices to say that if you're interested in these singular SPDs, Martin had actually a part in this paper on homogenization where he pointed out if you replace this by something of the form 1 over epsilon to the 3/2 g of, which was it, I think x over epsilon minus t over epsilon squared. So you see this parabolic scaling here, where g is a periodic function and centered, so everything's on a torus, the mean should be 0. Then actually, he can study this equation here as epsilon goes to 0, using his machinery, which is exactly passing through this picture up there. Right? There's a little twist here, namely, if you want to do this here, it turns out, as it stands, it will not converge at all, but you need to do something to the equation here, subtracting a suitable constant, and then you can get convergence, and he can identify exactly the limit. And I'm just writing this down to make my point here, that this effectively amounts to change the enhanced noise, and that induces an action on the equation here. So the strategy of proof here is precisely in this diagram. He takes this guy here, lifts this deterministic noise term here, lifts it up there, and checks that this phi here converges. Well, as it stands, it doesn't, but if you twist it a little bit, it does, and this twisting induces an action on the equation, and this twisted sort of lift does converge. And that's the same strategy that works in the KPC equation. Good. And from here, I think we should take a full stop here and take some time to talk about rough paths and how to make these pictures here precise. So here's my primer on rough paths. And so the starting object is a multidimensional path here, RD, smooth. And to any such smooth path, you can associate something which is of this form here. dxr. Okay. So if anything, you should notice is here there's a minus xs here. So as a consequence, you will not have any sort of additivity of increments. Okay. So it's not hard to find out what is the missing term to turn this into an equality, but it's not a additive linear relation. Okay. So in fact, you would have equality here if you take into account minus x 0s tensor x s t, and in this form it runs under Chen's relation. Right? But here's just a consequence of elementary computations on smooth paths. And, well, this is sometimes called a smooth rough path. Then you pick some Hölder exponent, pick or fix. And I'm just going to talk about the regime that applies to Brownian motion, so Hölder regularity between 1/3 and 1/2. If you're better than this, then you don't need all this. You can resort to Young type theory. But for this sort of alpha, it makes sense to define this space chi, the space, this enhanced noise space here, as follows. So basically, it's the closure, or the closure of such with respect to the following distance, okay, so this is the usual alpha Helder semi-norm. I'm not spelling it out. And here it would be, so that you've seen it once, the sup over xst minus y st divided by t. That's to the 2 alpha. The sup is taken over st on your time horizon 0 capital T. Okay, so this gives you a notion of distance between rough paths, so pairs of this form here. And now I want to point out this is a nonlinear space. Because such nonlinear relations, t minus s 2 alpha. Yeah. And here it's the same thing, xst minus yst divided by t minus s to the alpha, again, sup. And the notation here, of course, xst is the increment of the path xt. So this here is xsr. Okay, but this convention is only for the path increments. And these second order increments, as I pointed out here, they do not behave in this additive fashion. So here is the nonlinear space. This will do as a metric here. It doesn't really separate. I mean, it's the usual thing with Helder semi-norms. You don't separate constants from 0, right? So if you insist that this is done, you just add by hand plus, x0 minus y0 in norm or something like this. But in practice, it doesn't matter, because if you use these guys as drivers in differential equations, they come with a dx anyway, and so constants are x'd away. Now, there's a picture that I like very much. And okay. So there's a particularly cute interpretation of such rough paths, and it's also very convenient actually for this first homogenization problem that I talked about, this one. So let me very quickly tell you about this picture here. So any such rough path is actually a C alpha map from 0 t in the following space G2RD. And this is a metric space, and I will tell you in a second what they are. So this space G here is the exp of RD plus SOD. Now, you should think of this as the Lie algebra. Here's the exponential map, but I will spell it out completely for you. So this is like 1 V A plus V tensor square half, where V is in RD and A is in SOD. Yeah? And in this space here, so here you have something in RD, and here you have something in the D times D matrices. This corresponds exactly to X and mat bold X here. And I need a metric on this space here. So if you say Helder, I need a metric structure here, and G, has a metric structure, basically coming from G. So I take any element in this G here of the form x of v plus a, and then this is the so-called Carnot-Caratidori okay. So that's a fancy definition in terms of a control distance, but this is for all practical purposes what you need here. And if nothing else, you observe that on the second level here, you have this 1/2 here, and that corresponds exactly to this factor 2 here. Yeah. So the theorem is, I'm not going to prove it, I'm just telling you in a nutshell, that if you take any such rough path constructed from smooth paths, taking limits in this matrix here, you end up with an element which is C alpha with values in this Lie group here, C alpha with respect to the left invariant metric that comes from this Carnot-Caratidori norm. Okay? Now, why is any of this useful for homogenization? Well, I ask you for a little more patience here. I'm just finishing my prime on rough paths. So what can you do with all this? So in a nutshell, the main theorem of the theory, which of course is due to Terry-Lyons, is that there exists a unique extension of this ODE solution map y dot equals f y x dot from smooth x to rough. Right? And we're just seeing the tip of the iceberg here. I mean, it works for any alpha greater than 0, and you can do p variation and many other things, but let's not do that here. And as a consequence, you have a notion of rough differential equation, which is dy equals f of y dx. So if you come from this picture here that you just look at continuous extension, then this is just formal, but there's an intrinsic meaning. And it comes from, if you're used to numerical analysis of SDEs, you're surely familiar with the Euler scheme here. So if you are somewhere at some point, S say, and you want to make one step, what do? Well, you follow your nose. You look at the increment of your driving signal. You look, where are you at the starting point, f of ys, and this is the Euler step, right? But you can play this a little bit further, and let me emphasize the multidimensional nature here. Summation over repeated indices, of course. You can be a little bit smarter and say, let's do something like this. Again at y. And now we feed in this increment, the second order increment. Right? So this would be a Milstein scheme. It's an approximation if you want. And then you can turn this into definition and say, whenever you have something like this, plus something which is a little o of t minus s, then you call it the rough differential equation solution. Right? This is an honest definition of what you mean by solution due to Davies. Then you can check this is all consistent. So it's intrinsic meaning. The advantage of this one is you see immediately what happens when you start messing around with the second order information. Right. So the rough path here is a combination of the underlying path plus the second order information, which in a smooth setting you would always take canonically as the iterative integral, but you don't have to. So what happens when you start messing around, when you turn this into a different rough path that sits on top of the same path, but you change this one. For instance, think of a situation like this. You just imposed that on the second level you drift at constant speed, and so here take A in SOD, for instance, so that you preserve the chain rule. What will that do to you? Well, you plug it in here and have a look. What happens when you do a bar here? Well, you get the same thing as before, plus the same time here contracted with this matrix A, and then you get a delta t. So effectively, if this is antisymmetric and you contract it against these guys here, you get a leap bracket drift correction. If you make this correction here not antisymmetric but symmetric, which corresponds to the Ito-Stoyanovich case, you see the Ito-Stoyanovich correction here. So everything on a deterministic level. Now, I need to hurry, really hurry here. And suffices to say, when you play this game here with Brown in motion, and this guy comes from iterated Stoyanovich integration of Brown motion, then the solution here gives you a pathwise view on the Stoyanovich, solution to a stochastic differential equation. So there's some consistency that, of course, we want here. So let's go back. Let's go back here, and let's go back to this construction here. Namely, if you have a symmetric diffusion process here with a generator of this form, how do you construct the rough path associated to it? Well, there's a simple trick. I mean, in principle, you can, of course, go ahead, spell it out as an SDE, compute the iterated integrals, and have a look what it does, but it's a big mess. And it turns out there's a much neater way to do it. And namely, you give it directly a Markovian description, and so I'm a little bit pressed in time. So we have a Lie group structure here. So RD sits canonically embedded into this Lie algebra RD plus SOD, which you have seen up here. So in particular, I can define left invariant vector fields here that just coincide with the coordinate vector fields here at the origin, and then they use the group structure to move it around. So you get this UIs from the coordinate vector fields on RD, and then plus left invariance, plus group structure gives you left invariant vector fields. Okay. So if you take this as the identity matrix, what you would get is precisely the Markovian description, the generator of the sub of the Brown in motion on the step 2 nilpotent group, and the generator is, of course, the sub-Laplacian, this in Hermander form. This is what you see here. Okay, what's a good thing about this? This is accessible immediately to Dirichlet form theory. So you can just open the textbook. The three things you have to check is some topological consistency condition, then doubling, which is easy here, and then a weak Poincare inequality, which was long known here in this context. And once you have these three properties, this whole machinery, Dirichlet form theory, starts. In particular, you get heat kernels here with respect to the intrinsic metric associated to this Dirichlet form that you associate to this generator. And the intrinsic metric is precisely this Carnot metric that we had somewhere else. So now you have extremely good concentration of increments of this process here, namely Gaussian concentration. So you combine it with some Kolmogorov argument, you see immediately that here you have the C alpha Hölder regularity with respect to the Carnot metric, and this was precisely a description of our rough path. So rough path regularity at no work. Everything comes for free, provided you know this machinery. Moreover, everything comes uniformly in the ellipticity constants of A. So in particular, if you apply this to homogenization, these ellipticity constants don't change, and you get immediately tightness. Yeah? And then you have a little bit extra work to show that this would converge on a pointwise level to Brown motion plus iterated integrals, and combination of the two gives you convergence, weak convergence in a rough path space. And you go back to this question that we raised here in the beginning, right? And the answer is yes. Okay. So this was implemented by Antoine Lussier in a paper, I think 2010 or 2009, if you want to see some details here. And this Dirichlet construction, there are several references I'm happy to give you. Now I realize I have -1 minute left, but if you allow me, I will quickly return to this here. I have to ask it. the chair of the session. Thank you. Thank you. So I'll keep it below 3 minutes. So here, the answer is actually, I deleted the question, unfortunately. The answer is no. Right? There the answer was yes, but here the answer is no. And the reason is that the presence of this magnetic field here, this antisymmetric part of M, introduces a certain spinning on small scales. So it doesn't affect the limit of xm. It's still a Brownian motion with the correct covariance structure, but it does actually mess with the second order information. So the precise theorem here is, so here's the theorem. But let me switch to a, let me restate this as m times xm converges to p, and now p is a standard Brownian motion, so we don't have to. So the theorem here is that if you look at m xm, and again this is a, has C1 sample path, so I can compute the iterated integral as a classical Riemann-Stieltjes integral. And so the convergence here is Brownian motion, and then it's B bar, where I need some space here. Where B bar ST is actually right. So this is what you would expect. If you think of Stratonovich, smoothing, mollifying Gibson Stratonovich, this is what you would get. But in fact, what you get is something else, namely a correction term of this form here, where this is indeed in SOD. So it's precisely of the form that I discussed briefly here. So in particular, the effect on a, if you plug this physical Brownian motion in a magnetic field, if you use it as a driver in a subsequent differential equation, what you will see here is that you pick up an additional Lie bracket drift vector field, and then you can amuse yourself and compute what this A is precisely, and there's a closed form. There's a closed form expression, which is pretty if you assume that M is normal, so that it commutes with its transpose, and in this case, there's a simple expression, namely it's the antisymmetric part of M times the symmetric part of M minus 1 here. And so in particular, you see explicitly from this expression, when the antisymmetric part is actually 0, there's no correction. Right? So it's really the magnetic field which is responsible for this. And if M is not normal, again, that's an expression which is harder to write on the blackboard. I mean, it's still explicit closed form. Okay, so this is it. Thank you very much.
So there is some question. They ask, since it is recorded.
Okay. So you defined the rough path by this integral, which is on this hidden blackboard, and so you say that in all these examples like homogenization, filter problem, and others, you can represent it in this form. Yeah? Rough path you can represent as such integral from smooth path.
With some disclaimers, okay? So if you come from smooth approximations, may they be like this, or in fact you come from, I mean, even here we have sort of hardwired a Stratonovich setting by working in this Lie group. I didn't want to go into details on this, but there's a chain rule hidden here. So in all these examples, you're indeed in this setting here, so you can get there by you know, completion of smooth paths in this rough path metric.
By this formula.
Pardon?
By this formula.
This here?
No.
The one above? So this only works. I mean, this is a definition that works provided X is smooth enough that this makes sense.
But it works in all these examples which we did.
Well, there are very yes and no. I mean, if X is a semi-martingale, like in this first example over there, right, then you have to make a choice. You want to use Ito, backward, Stratonovich. It's not clear a priori. So if you have smooth sample paths, yes, you can use this. Well, here's one example that may clarify it. Think of the following sequence of smooth paths in R2, which I identify with the complex plane. Right? And the way I prescribe them is to say it's e to the 2 pi I t, then we spin around n squared times, at the same time I scale it with 1 over n. So clearly as n goes to infinity, this guy here goes to 0 uniformly. Yeah? But what happens to these iterated integrals? Well, there's a geometric interpretation here. If you think of the antisymmetric part here, it has an interpretation of the area. So if this is the underlying curve x, and here's s and here's t, then the antisymmetric part of the second order increment has the interpretation of assigned area here. Just, you know, application of Stokes or Green's theorem or whatever you call it. And in this example here, every time you spin around, you get area of the order 1 over n squared, and you do it n squared times, so the area is not going to disappear. So my point is, if you compute here, if you compute your xn according to this rule here, then it will converge in this rough path space to something which is 0 here on the path level, which is the, you know, the pointless limit here. But on the second order level, you will see something, and it will be something like 0, then some constant t minus ct, and this constant has to do with pi or something. Yeah.
So the trick lies how you interpret this cross in the integral. Yeah?
Pardon?
The trick lies how you interpret this cross in the integral. That's
ultimately, you should read this definition the other way around. Someone gives you, in some axiomatic fashion, this here, and then you use this to define the meaning of these iterated integrals. And so this is a particular example. Of course, you cannot take 0, integrate against 0, and recover this one.
So there is some other question.
If I may,
Yeah, of course.
I'm missing a reference to one of my former postdocs here. This discussion here was worked out in great detail in a paper by Paul Garcia, who is now at Dauphine, and Terry Lyons and myself. And perhaps interesting for homogenization people, I mean, this is a nice setup because everything is Gaussian, so you can compute everything. This makes it, you know, pleasant, of course. But you're not restricted to this. I mean, it's perfectly sensible to assume that your, you know, frictions and magnetic fields depend on where you are in space, and perhaps the noise depends where you are in space, and so you may want to redo this whole analysis in a local fashion. So you can do that. There's some remarks in the paper about this. Okay.
So let's thank the speaker again.